You can see what I'm sharing, yeah?
Yes.
Now, so I want us just to begin from how we left yesterday. We had looked at this algorithm of RSA, and we were looking at the first example, and I think there was some problem with the internet, but I will still go through the algorithm. Then after that, again, we'll look at that example and look at other examples. Now, so I said, for example, supposing it's you that wants to send a communication to your friend. So your friend is to receive communication from you. So if that is the case, then your friend is the one to set the public keys and then send to you. There are two public keys that your friend is supposed to create and then send it to you. So the first thing your friend will do will pick two prime numbers, P and Q, and we said they should not be equal. Then after picking those two prime numbers, your friend will then get their product. This product, M, becomes the first key your friend is supposed to publicize. And then the P and Q are supposed to be private, so he keeps them private. Then using P and Q, your friend again will calculate phi of M. And we know what phi of M is. These are number of integers less than M, but relatively prime to M. So your friend calculates what phi of M is. And if you are dealing with the two prime numbers, it's just easy. Your friend does P minus 1 times Q minus 1, because those are prime numbers. So it becomes very easy to find the phi of M. Then after that, your friend chooses a number which is relatively prime to phi of M, supposed to be relatively prime to phi of M. That one you just choose, the friend just chooses, it doesn't calculate. We said because you're making a program, then you're supposed to know that the GCD of E and phi of M is supposed to be 1. That is what we mean when we say they're relatively prime or co-prime. That's what it means, that those E must be, the GCD of E and phi of M should be 1. Now, so after choosing that number, then what follows is now a calculation. Your friend gets the inverse of that E, finds the inverse of E, and that inverse of E, we call it D. So that will be a private key. He will not display it, he will not let anyone know what it is. Just a minute, let me scroll up a bit. Now, so to find this D, we've said that this is the inverse of E. Your friend has two options. The first option, he may want to use the extended Euclidean algorithm, or he may want to use the Euler's theorem, because your friend has those two methods. And we said yesterday that this time it's not possible for him to use the Fermat's little theorem, because this phi of M is not prime. So he's doing this using either the extended Euclid's algorithm or is using the Euler's theorem to find D. You see what is written here? It's written that find D such that E times D gives you 1. That's what is written here. So what it means is that D here is the inverse of E, and E is also the inverse of D. So that's what this sentence means, that E times D should give you 1. In other words, they should be inverses of each other. Now, after finding that D, your friend has done almost everything. He keeps the D private. He keeps P private. He keeps Q private. So P, Q, and D are kept private. And in fact, he's also supposed to make Q of M private. Because if anybody gets access of this Q of M, and using this, knowing that Q of M comes from these two prime numbers, and using this formula, somebody is likely to maneuver and find what P and Q is. So phi of M is also supposed to be private. Most books only talk of these three to be private, but when you continue reading, you discover that anybody getting access to this phi of M may be able to know what P is and what Q is. And since E is public, this person, once he gets to know what P is and what Q is, this person, and again, M is also public. So once he gets this, he's able also to get D. He's able to get D once if he gets access to this phi of M. So phi of M is also supposed to be private. But what your friend is supposed to make public is then M and D. Now, so your friend has made M and D, no, M and E, not M and D, M and E. He has made M and E public. You want to send him a message. What you'll do, your message, let me say your message maybe is X. If your message is X, take this X and raise it to E. This is the message you send to your friend. This is the ciphertext. X here is the plain text. So the ciphertext now is Y, which you get by X raised to E. Once your friend gets the E, the Y is supposed to decrypt it. So to decrypt this Y, he raises it to the inverse of X, the inverse of E, which is D. And this gives him the message you sent, which is now the plain text, which was X. Your friend is able to read that. So we had gone through that algorithm yesterday, and we were just looking at an example. In fact, that was the second example we're looking at, because the first one we had looked at it before looking at this algorithm. So let me just go to that example that we were looking at. It's below this algorithm. The algorithm we've already seen it. It's here. The encryption and the decryption. Now, so I was now talking of this guy called Alex. He has these two prime numbers. Just a minute. It's okay, it's okay. So he has this two, he has chosen P to be. So this is the guy who is supposed to get the message. This is the guy who is supposed to get the message. So he has a role to pick a P and pick a Q. The other role that he has to do is to find their product, the product of those two. The other role that he is supposed also to do is to pick a number which is relatively prime to phi of M. So in fact, he's supposed to first of all find what phi of M is, and phi of M is 11 minus 1 multiplied by 17 minus 1, which is 160. Then picks a number which is relatively prime to this. He has decided to choose 7 because the GCD of 7 and 160 is 1. So he has done the right choice. Now, after choosing that 7, he has another role to get its inverse, to get the inverse of that 7. That will be almost the last role. Then in fact, that role he can do it after receiving the message from you, because that one is not urgent. But he can just do it early and keep it. There's no problem. So how do you get the inverse of 7? We've said there are 2 ways. We want to get an X, or let's just continue calling it D, such that this gives you 1 mod phi of M, and phi of M we found it to be 160, mod 160. So we find a D, you just write this D properly. So you're supposed to find a D. So just solving for D here. You can do this using the Euclidean algorithm, or you can do it using the Euler's theorem. If you are to do it using Euler's theorem, then you remember that it's supposed to be 7 raised to phi of 160 minus 1. Then mod 160. This is what gives you the inverse of 7. So you're supposed to get phi of 160. I think yesterday we did that. I remember, was it 64? I think we got it to be 64, so that you are doing 7 raised to 63 mod. I don't know whether it was 160, whether it was that 64. Let me just confirm. But we can do it. Let's just do it. We had done it yesterday. So 2 goes there 80, 2 goes there 40, 2 goes there 20, 2 goes there 10, 2 goes there 5, and 5 goes there 1, so that the prime factors of 160, they are just 2 and 5. So to get phi of 160, therefore, is a half times 4 out of 5, then times 160. Times 160. That gives you what? 64. That gives you 64. 64 minus 1 gives you 63. Mod 160. This, you can do it using the first powering algorithm. First powering algorithm that we learned. So this is one way of finding that inverse. You'll find it to be 23. You'll find that inverse to be 23. The other way, you can use the extended Euclid's algorithm. And I just want to remind, if anybody has forgotten what we were doing, to do that, you are repeatedly dividing 7 into 160. So you would say 7 goes into 160 how many times? Plus what is the remainder? That remainder. And then this remainder goes into what is here, how many times, and so on. That's what we are doing. You just you'll have to recall that. And then that is the Euclidean algorithm. Then you reverse, and when you reverse, that is the extended Euclidean algorithm. Now, so now Alex is now done. He has done what he was supposed to do. He now waits for anybody who will want to send him a message. Once he makes his keys public, anybody, he doesn't need to make another key for another person. Just makes once, and in his lifetime, that will be the key. So anybody who wants to send him a message would be using that key. So his key is now this one, the public key. That is M no, n, the product of those two numbers and the e, and the e. The product of those two numbers was 187, and the e is that. This is the public key. This is the key anyone who wants to send him a message would use to encrypt the message. And then this will now be his private key. He'll use this to encrypt, not to decrypt the message. To decrypt the message. Let's say Wanjiru wants to send Alex a message, and the message Wanjiru wants to send is 91. So Wanjiru will not send 91. She will first of all encrypt it. So to encrypt 91, when Jill raises that 91, first of all, she checks what the public key is for Alex. Alex may have announced this through media or another channel. So when Jill gets it, and then the 91 that she wants to send to Alex, she raises that to 7. Then mod 187. This, you do it using the fast powering algorithm. That's what we were doing yesterday before we went off. So you do it using the fast powering algorithm. And when you do that, you would then get 31. So 31 is the message that Wanjiru then sends to Alex. When Alex receives this 31, he's supposed to decrypt it so that to know Wanjiru's initial message. So to decrypt, he's going to use this key. The 23 and the mod is that. So this is 31 raised 23 mod 187. He gets 91, the message that Wanjiru wanted to send. So that is how you do this. We shall look at another method, another example. Now, so I've already said that this, once Alex has announced this key, he doesn't need to announce another key another day. Anybody who may want to send him a message at any given point, that person is just supposed to go and check where Alex public key is, and then get the public key and use it to send a message to Alex. Let's say this time there's somebody else here. Just a minute, this thing. So example 2 here, let's say Ocheng also knows the message that knows the key to Alex, and he feels that he's supposed to send Alex a message, no. Supposed to send no to Alex. And because he doesn't want anybody else to know that he sent him this message, no, he encrypts it. So first of all, this is now a sentence. You see, when Jiro earlier was sending a figure, and the figure was 91. So this RSA works with the figures. It works with the figures, so digits. What Ocheng is supposed to do is supposed to convert this to digits. In my example, I've used conversion. Conversion I was using was that A is mapped to 0. I'm using the alphabet. C is mapped to 2, D is 3, all the way up to N, and N was 13. N was 13 and O was 14. So when you change the alphabets to the numbers, so A goes to 0, B is mapped to 1, C is mapped to 2, D is mapped to 3, and so on, and up to Z mapped to 25, because there are 26 alphabet. So Z is mapped to 25. There are other conversions. Programs have other conversions. But this is the one I used. I was using the alphabets. Now, so that means Ocheng has this duty, first of all. The first duty Ocheng has is to find out what the public key for Alex is. And now he has it. For this example, I decided that the public key for Alex is above there. It was 187 and 7. This is a public key. So anybody who wants to send a message to Alex must know what this public key is. So Ocheng has found it. Wants to send him a message. So he has the first duty Ocheng has, convert these to numbers. So I've said he has to change every letter to a number. And for instance, I've said A is mapped to 0, and B is mapped to 1, and C is mapped to 2. But now, when you're converting to numbers, you make 2 digits. So if it's A is mapped to 0, let it be 0, 0. And B be mapped to 0, 1. And C is mapped to 0, 2. And D will be mapped to 0, 3, and so on. So we use 2 digits when you are converting these letters to numbers. Now, after converting, there is the condition when you are working this, that the number that you want to send is supposed to be less than M. Supposed to be less than M minus 1. Supposed to be less than M minus 1. So it's where M is this is our M. 187. So the number you're supposed to choose, you see, for Wanjiru, it was easier. Wanjiru was just sending 91. 91 is already less than M minus 1, which is 186. And it's supposed to be greater than 1. Now, look at this. The one that Ocheng wants to send is greater than M minus 1. So in that case, you would break your number into digits which are lesser than M minus 1. You break your number, you can break it as 13 and then 14. When you break it as 13 and 14, you encrypt each one separately. Each of this block is encrypted separately. And then what you get, you send it again separately for him to decrypt it, them separately that way. And then after decrypting, he'll just join the results. So we've discovered this number is greater than M minus 1. We separate, we break the number into 2. You can break, if it's a long number, you break it the way you want. Let me say you had 13, 14, 19, 20, 25. So if your M is 187, I can even break it here. 131, which is less than 186. But I can say 419 would be greater. So this one, I can break it here so that I have 41. Because if I break it at this 9, it would be greater than M minus 1. This is 92. 92 here. I have an opportunity to break at 2, but that one will not be wise because the other one will begin with a 0. So I want to avoid that beginning with a 0. So let me just break it at 9. And then this one, I break it as 20. And this other one, I break it as 15. Break it as 15. Then after breaking that, what you now do, you go to the public, where the public key is. You have these 7, encrypt each of these blocks. So we had found these 2. Encrypt the first one. You get 106 when you use the fast powering algorithm. Then now the second one, again, you get 108. You have these 2 messages. That these are the encrypted messages. Send them this way. You don't join them. Just send them separately the way they are. When Alex finds this, he will decrypt the first one. Remember, his key was 187 and the D was 23. So this 23 he raises to each of these. Using the fast powering algorithm, he would get 13. And then this other one, using the fast powering algorithm, he'll get 14. So now he has found 13 and 14. He'll go back to the alphabet and find out what 13 is, and then find out what 14 is. And he has the message no that Ocheng wanted him to read. So sometimes it's a very long sentence. When it's a very long sentence, he would try to supply it with the breaks and punctuations so that he gets the meaning that Ocheng wanted him to get. So that is how you do it if it is a sentence. Now, I'm not going through the fast powering algorithm because I know we did that in one of our lectures, but I can do one here because I can see a shorter one. Let me do the shorter one, 14 raised to 7. Then this 13 raised to 7. This one I can do it because they're short. But then you can do the raised to 23. That one you can do it later and see what you get. Let's just do this one because it's short. What we said, it will be 13 raised to 1. We are doing it mod 187. That will be 13. Then 13 raised to 2. That will be 169. 169 is smaller than 187, so we just write it. 169. So what about 13 raised to 4? 13 raised to 4 is the same as just squaring this line. Because when you square this line here, you get 13 raised to 4. And this other one is 169 square. I use my calculator. (169 square). 169 times 169, you get 28,561. Then divided by the mod, which is 187. It goes the 152 times. Get the remainder. The remainder is 137. Now, if I square this one again, I'll get 30 raised to 8, which I don't require. What I require is 30 raised to 7. So then I can say 13 raised to 7, therefore, the same as 13 raised to 4, this 4 plus that 2 plus that 1, because this is 6 plus that is 7, which is the same as 13 raised to 4 times 13 raised to 2 times 13 raised to 1. But 13 raised to 4 is 137. And 13 raised to 2 is 169. And 13 raised to 1 is 13. Get this product and divide it by the mod, which is 187. So let me get the product. 137 times 169 times 13. I'm getting something like 300,989. divided by the mod, which is 187. It goes there 1,609. 1,609. 1,609. Now, when you get the remainder is 106. The remainder is 106. That's what we got there. So this is the first pairing algorithm. We had gone through it. Maybe one of the Thursdays we'll want to again go through it, again just repeat it and see, so that we can also have people writing programs on how to use it in getting these modes, getting remainders. Because it's a very good method. Every time you're using even the Euclidean algorithm and what, you may want to again use it somewhere so that you can move faster. So maybe we can repeat it one of the Thursdays. Let's look at another example. So I want us to look at the next example. It is here. So this time it's you choosing. You've chosen 2 primes. That means it's you will be receiving messages from people. So you've chosen P and Q to be 7 and 11. So since it's you, then get the product of those 2 numbers and get phi of 77. Get phi of 77, which will just be 7 minus 1 times that, which is 60. Then look for a number which is not relatively prime to 60. And that number you've chosen, 17. Number which is, in fact, the easiest way to get number which is not relatively prime to 60 is this way. Once I have the 60, I try to get its prime factors. This is 30, this is 15, this is 3, 5 there, and 1. So I can see that 60 is the same as 2 raised to 2 times 3 times 5. So I choose any number that is not here, is not a factor here. Any number that is not a factor here and is less than 60. I choose, that is now the number which is relatively prime to 60. So I've looked at these factors and I've seen 17 is not here. So I choose it to be my E. I would even have chosen, which one? 4 is there.
Which is 11.
I could even have chosen 11. Yes, that's correct. I could even have chosen what else? Even 7. But not 4, not 6. Because you can see 6, 3 can go into 6. 4, 2 can go into 4. I cannot choose 9. I cannot choose 10. Because 5 can go into 10, 2 can go there. I could even have chosen what else? Even 13, even 17, and so on. Now, so it's not difficult choosing E. You just need to know which numbers are relatively prime to 60 there. So I've chosen 17. So since it's us now who wants to get the message, after choosing this 17, we then supposed to get the inverse of 17 mod phi of 60. So remember, that is the only time you're using this mod. That's the only time you're using this mod. Remember that. It's the only time you're using this mod, when you're getting the inverse of 17. But going further, when you're encrypting, the mod is 77. This 77. And when the guy gets the message, when he's decrypting, again, the mod a 77. So let's not confuse these two. But when you are getting D, the mod is phi of 60, phi of M. Not phi of M, phi of 60. Phi of 60. Because phi of M is what gave us 60. Oh, yes. So the mod is phi of 5 forward. Actually, it's supposed to be phi of M. It's supposed to be phi of M, not phi of 60. Which then gives you 60. So this one is not correct here. It's supposed to be phi of M. This part is supposed to be phi of M, which gives you 60. This is correct. This is correct. So the only part that is not correct is this. It's supposed to be phi of M here, not 60. Now, so we want to get the inverse of E, and our E we've chosen to be 17. And I think that point is home. The point I wanted to make is that mod, when you're using mod, the only time we're using mod of phi of M is when you're getting the inverse. When you're getting the inverse of E, the mod is phi of M. So you're getting the inverse of E, mod phi of M. But going further, our mod will be M, not phi of M, will be M. So when you're decrypting and when you're encrypting, that's the point I wanted to emphasize. Let's find the inverse of 17. And we've said there are two ways. We may want to use the Euler's theorem, which I've used here. And Euler's theorem says that the inverse of 17 is 17 raised to phi of M, now phi of 60, phi of 60 minus 1 mod 60. If you don't want to do that, because we've used Euler's theorem in the previous example, let's this time use the extended Euclidean algorithm, which still does the same thing of finding the inverse. So the extended Euclidean algorithm says we want to find 17 times D, which is congruent to 1 mod 60. So we want to find what D is. We want to find this, we want to solve this, this equation here. So then this equation has only one equation, has only one solution because the GCD of 60 and 17 is 1. So it has only one solution. So you would then say 17 into 60, how many times? Let me just do that, the first part, and then you can do the rest. So 17 into 60, just a minute. Just take 60, divided by 17, it goes there 3 times. So this is 3, because 17 goes there 3 times. And what is the remainder? What is the remainder? The remainder is 9. Then what about 9 into 17? What about 9 into 17? It goes there once, and the remainder is 8. What about 8 into 9? It goes there once, and the remainder is 1. Once you reach where the remainder is 1, this is then the GCD, because it means the next part, the remainder will be 0. Then you make this one the subject of the formula. You say, what is 1? 1 is 9 minus 1 multiplied by 8, which is 9 minus, now you replace this 8. You replace this 8. This 8 is the same as 17 minus 1 multiplied by 9. 1 multiplied by 9. What does this give you? This is 9 here, and then open the bracket. Open the bracket with this negative 1. You'll have negative 1 multiplied by 17. And then negative times negative will be positive 1 multiplied by 9. Collecting like terms, the 9s together, you have negative 1 here multiplied by 17, and then plus 2 multiplied by 9. Where did I get the 2 from? I just factorized 9 outside, and 9 goes into itself once. And this one, this other 9 here, goes into that again once. So that 2 is this. Now, so we now replace this other remainder. So what do we have? Negative 1 multiplied by 17 plus 2 into, this remainder is 60 minus 3 multiplied by 17. Open that bracket, and before that you have negative 1 multiplied by 17, and this will be plus 2 multiplied by 60, and this other one will be negative 6 multiplied by 17. Like terms together, let me begin with the 2 multiplied by 60, and this other one is negative 7 multiplied by 17. Okay, let me create some space. Okay, that space is enough. So we've then found that 1 can be written as 2 times 60 plus 17 times negative 7. What we wanted was the inverse of 17. So that means that the inverse of 17, therefore, is this negative 7 mod 60. So what we were doing last time, we were just, since this number is less than 60, we're just adding it to 60, and we're finding that this will be 53 mod 60. So in other words, the inverse of 17 is 53. That is our D. That's our D. So I think you can follow the steps when you listen to the video, because you can see they are mixed here. But when you're following the video, you're following the way they write, and then you can see what was written first. Now, so we found that 53 is the inverse. 53 is the inverse. What we've used is the extended Euclidean algorithm. But what I used in this example is the Euler theorem. And all the two, we've learned all the two. So it's easier for you to apply them. Yesterday, we saw some application of the Euclidean algorithm. So again, we need also to see the one for the Euler theorem and all those other things, so that we can move forward well. Now, so we found D to be 53. So what are our keys? Remember, it was us that are supposed to receive the message. So we kept this and this private. So we had to make 77 public and also make E public. So this is the encryption key. Encryption key. And then we found D. We make D private. Nobody should know it. That will be our decryption key. So our decryption key is this one. So this encryption key, we make it public. Anybody who wants to send us a message, let him use it. And we don't tell anybody what it is, or what the private one is, the decryption key. That one remains ours. Now let's see if there's anybody who wants to send us a message and see what that person will have to do. Yeah, there's somebody who wants to send us a message. And the message the person wants to send us is 8. So what this person is supposed to do is supposed to encrypt this. So the private, our public key, which had, was it 17? Mod, do you remember, this is the point I was emphasizing, mod 77. Then using the extended, using the fast powering algorithm, the person computes this and he gets 57. This 57 is what he sends to us. So it's us now to decrypt it. We take this 57 and raise it to our private key, which was 53, mod 77, and use the fast powering algorithm to get 8, which was his plain text that he wanted us to read. Now, just a question. Can you still hear me?
Yes.
It's okay. So let's continue. There's this lady that wants to receive messages from people. So she creates a public key and her private key. She has chosen 311 as P, and then she has chosen user Q. She'll have to calculate M. And then she'll also have to calculate phi of N, which is just 310 times 366. She gets that. Then she looks for a number which is relatively prime to this. A number which is relatively prime to this. She has decided to choose a bigger number. It's always good to choose these bigger numbers for security reasons. And even these prime numbers, this one is just a very small number. It's supposed to be very big, one that only a computer will do. Only a computer can work with. And so that when you multiply those two, then even a computer will not factorize that number. And if it was to do it, it is supposed to take ages to factorize. Not something that a computer can factorize in a few minutes. It's supposed to take ages, so that it begins factorizing today, and then it factorizes until we leave this earth, so that you are sure that your information is still secure. Nobody can factorize that. So you see, the only way you can break the RSA is by factorizing M. Because M, you know it. The other thing you know is E. But E can only help you once you factorize M to find P and Q. And once you find P and Q, you can now try to maneuver and see what find phi. You see, P and Q will assist you to find phi of M, for instance. And then if you have this, then you can find what the D is. You can find what D is and so on. But now the thing is, this M is supposed to be, this P is supposed to be very huge, Q is supposed to be very huge, so that nobody can factorize. If you don't want to factorize, the other way is now to use guesswork. Try and use guesswork, that maybe the plain text was this, maybe this cipher text is this, or this, or this, or this, and that will take you a very long time if you are a hacker, or somebody who wants to attack and find information. Now, so what she wants to send is the word okay. No, this is somebody wants to send her. She has chosen these numbers. She has chosen E. So there's this guy called Teddy who wants to send her the word okay. And Teddy knows the public key to Jennifer, which comprises of E and N. These ones are made public by Jennifer. These two are made public by Jennifer. So Teddy is supposed to encrypt a message and send. So what he does, as we said earlier, this okay has to be converted to numbers. And when I converted, I found O was 14 and K was 10. So this number is 1410. Now it's supposed to be less than M minus 1. If it's bigger than M minus 1, as we said earlier, we break it into some blocks. Fortunately, this number is less because our M, where is the M? This is the number here, 11, 41, 37, our N. So that means this one can be sent, we can encrypt it the way it is without breaking it. But if you wanted to break, there's no problem. You'll still get the same result. And remember, if you are to break it, then you have to send those blocks individually. You send all the blocks, but you don't unite the blocks. Now, so he obtains the public key, 343, raises it to 1410, and uses the fast powering algorithm. And when he does that, what does he get? Let me just erase this. So this is a huge number. We may not go through. We may not do it, but I think maybe I did it. Yes, I did it using the fast powering algorithm. So remember this fast powering algorithm, there's something I told you earlier, that it's always easy to know how many times, if you're writing a program, supposed to know how many times are you going to square these numbers. And what is telling us how many times is this power? This power, which is decimal, you convert it to binary. Convert it to binary. Let's just see what the conversion is. Let me find out what the conversion is to binary. This is 343. To binary is 1, 0, 1, 0, 1, 0, 1, 1, 1. Let me see what Okay, that is what we get. So that means 1, 2, 3, 4, 5, 6, 7, 8, 9. We shall square 9 times. Let's see how many times I've done that. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the number of times I've done that. So if you're writing a program, maybe this will assist you, because you may want to maybe tell the program the n, the number of n, how many times are you going to do that? So maybe this n is equals to what? To 9. Maybe that's how you do it. So that you tell it you're going to do it 9 times. And you're squaring the one above, the one above. So for example, if I have this one, to get the next one, I square the first one here. I get this. Then when I square this, I get this. When I square this, I get this. When I square that, I get that. I square this, get that. Square this, get that. Square this, get that. And so on up to the 9th time. And we are doing this mode M. M was above. So that's how we do the fast powering algorithm. And look at what I did here. How many have I added? I've added 1, 2, 3, 4, 5, 6. Yes, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. The one without zeros. The one without zeros. How many? The one that are not zeros. 1. In fact, you will just have done this one. You'll just have done these ones and omitted the zeros. Because this is the first one. This is the first one, which is here. And then the second one is here, which is there, number 2. And then the third one is here. The third one is here, which is there. Then from there, we skip the one that is a 0. And then we come, that is 1, 2, 3. We skip the 4th one. We come to the 5th. The 5th. 1, 2, 3, 4. The 5th has power 16. And then we skip the 7th. We skip the 7th. We come to the 8th, power 64. And then we skip this and come to this. And that is what you're seeing here. That's what you're seeing here. So the first one, this is the first one, second. See, when you are doing your place values, you begin from this side, going this side. So this will be the first, second, and so on. And they're the ones you'll be seeing here. That means you can even minimize. You can even minimize the number of multiplications you have here. And I have included all of them because for easier, because I've included all of them because I know that I'll be squaring the subsequent one, the earlier one, to get the second one. But if you're using a computer, how are we doing it? We're doing it this way. Let me just see what we are doing. We're doing a raised to 2, then raised to I. A raised to 2, then raised to I. So what we mean, our n, it's this. Our A is this. 14, 10. Raise this to 2. And I begins with a 0. I begins with a 0. So I is 0, 1, 2, 3, up to 8. Because how many are they? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I is 1, 0, up to 8. These are nine numbers. Those are 9 numbers. So now I want now to use a program. I think this one will help. This one will help if we're using a program. If we are writing a program, I think that will help. And then now you know that we'll only look at what is here, what is ones, the ones, and we'll omit the zeros. So I can just come straight away, and having known that, I'll just do the first one, which is this. That is 1410 raised to 2 raised to I is 0. So 2 raised to 0 is 1. So what we have here is just 1410 raised to 1. And then that is when I is 0. The second one is when I is 1. This one, when I is 1. When I is 1, we have 1410 2 raised to 1, which is 1410 square. So that's what I did here. And you get 47,771. And then the next one, when I is, we've done when I is 0, when I is 1, we now do when I is 2, it'll be 1410 raised to 2, then raised to 2. 2 raised to 2 is 4. So this is the same as 1410 raised to 4, which is the same as squaring this, because this one is squared. So when you raise to 4, and that is what you get what I have here. So you've done I2. You now go to, this was I0, I1, I2. We skip I3, and we come to I4. So that is A raised to 2 raised to 4. What is 2 raised to 4? No, in fact, you do it this way. What I know is this. What we know is if you have A raised to M, then raise it to N, this is the same as A raised to Mn. The same as A raised to Mn. So this is the same as A raised to 8. That's it? No. It's not the same thing. It's not the same thing. This one is not the same thing, because what I'm doing here, I'm not taking the whole thing and then raise. What I have is supposed to be M raised to N. M raised to N, because it's 2 raised to I. It's the 2 we are raising to I, not the entire thing. It's the 2 we are raising to I. So that means this is supposed to be 16. This is supposed to be 16. 2 4 times. 2 4 times. That would be 16. And then next, we've done when I is 3, 0, 1, 2, 0, 1, 2, 3. We've done when it's 4. So now we skip 5 and do when I is 6. That is A raised to 2 raised to 6. That is 2 6 times. 2 6 times. That is 2 times 2 times 2 times 2 times 2 times 2. This is 8, and this is 8. That gives us 64, and so on. Now, so maybe when we get time again, we shall look at that, so that you can see how easily you can write a program to do that. Shall revisit that and see what to do there. I want us to look at the next example, because I wanted us to look at how to make signatures using this RSA. We have other ways. I want us to use RSA to make signatures. Now, so this one, now, so this will just go through it. It's just the same working we've done before. It's decrypting and encrypting that we've done before. So I've done all of this. So the working is being recorded. This is the working until we have the plain text. There's a bit long because we are dealing with the bigger numbers. So then interprets the word okay. Now you'll go through this working again. I've now made the sentence a bit longer. And why was I doing that? Just to show you how you break the words if they're bigger than the mod. That is what I wanted to emphasize. But the logic is the same thing. The thing is, I wanted this number to be bigger than the mod so that you break it. And this is what the number gave me when I converted it. When I converted the word love maths, converted to numbers, this is what I got, a very long number. Then, what was my n minus 1? What is my n, first of all? Oh, we are sending to Jennifer. We're sending to Jennifer. We have Jennifer's public key above in example 4. So we have her public key above. So that is the public key we'll be using. So this word loves math gives me this, a very huge number. So I then broke it here. Remember how we were breaking it the other time? We were avoiding beginning with a 0. Because we are raising this number, we are raising it to another number. When you begin with a 0, that 0 disappears. We don't want to lose it. So this is how I break. So it's not a must they should be the same number of digits. You're just avoiding to a number beginning with a 0, because I know that when I begin with a 0 and raise it to another number, this 0 will disappear. And it's part of the text. So I don't want to lose it. So that's what I wanted. But the working is the same thing. I just want to understand this breaking bit. Then after breaking, now you doing your encrypting. You encrypt each of the blocks separately. Each of the blocks separately. You can see that I've encrypted the first block, gives me that. Then the second block gives me this. Then the third block gives me that. Then the fourth block gives me this. Then those what I get, I send it again as a block. I don't join them. I send them as blocks separately. So when Jennifer gets, she decrypts each of these blocks. She's now decrypting. You can see she decrypts the first one, then decrypts the second one, then decrypts the third, decrypts the fourth. Then after that, she can now join them. She can now join them to make one long thing. And then she also knows that these things were, when you are converting from letters to numbers, you are writing the numbers, they were 2. Like A was written as 00. So she knows that this is one letter. This is another letter. This is another letter. This will be another letter. So that's what she does. That's what she does. She knows that the numbers are in pairs of 2. Now after that, she's able to read the word love maths. Then it applies the commas or the spacing and so on. Now, cryptanalysis, this is a process of, if you don't know you don't know the key, and you want to read the message. So you are trying to attack. This is what we call cryptanalysis. Maybe we look at it next time. Then after that, we look at the RSA key. Thank you.